This is 4.3 Logarithmic Properties, Part 1. All right, so this slide is just a real-world example of when we use logs, when we talk about the acidity of something or the alkalinity, we can use logs. Also, the second slide, we talk about decibels and sound. You guys actually have a word problem here that will use logs that's dealing with sound. So we'll get to that later. All right, so the first property for logarithms is the product rule. So I want us to think back to when we did rules on exponents, right? And we had the product rule for exponents. And the product rule said that when we multiply the same bases, then we would just take that one base and we'd add our exponents. So there was this connection between, okay, when we're multiplying those same bases, then we're gonna just add the exponents, right? Well, you have something similar here in the sense that when we have multiplication inside of the log, right? So we see multiplication right here. It's actually the addition, so the sum of the logarithms. So notice that we were able to expand that logarithm from log base b of m times n to log base b of m plus log base b of n. But notice that log base b is on both of them. So they give you an example down here. They say, okay, remember ln is the same as log base e. So ln, the natural log of 7 times x, would be the same as the natural log of x plus the natural log of 7. And this would be considered expanding the logarithmic expression. They could have given us this and then told us to condense it. So we'll be doing using these rules later to expand and condense these logarithmic expressions. So that's the first rule, the product rule. So let's go ahead and apply that. So here I don't have a base. So remember that if I don't have a base, I understand this to be a common log. I understand that base to be 10. So I'm just going to still take that base and expand it, and it's going to go to each factor in the log. So log 3 plus log x plus log y. And when they tell me to expand the logarithm, I just think of like an accordion, right? It's like it looks all squished up, but then when I pull on the ends of that accordion, it expands it out and separates all those sections. Just make sure that you put log before each of the factors inside the original logarithm. Okay, so same thing here, except now we have log base 5. And write this a little bit bigger first. Okay, so let's go ahead and expand it. Here's my two factors. Log base 5 of 125 plus log base 5 of x. So I already completely pull it out and expand it as much as possible, but now I need to simplify any parts. That's what I was looking for in there, and I'm still not seeing those exact words, but we want to simplify. So remember in the last, with the last slides, I mentioned how sometimes if we can get it down to an integer, then that's what you're going to go for. Well, this right here can simplify down to an integer, and you can put that in your calculator. So let's go ahead and plug that into the calculator. So log in my main screen will be math, so F4, and then F2 for log AB. Okay, and that gives me the box. Remember, if I use this button right here, that just says log, it's going to give me the common log. So it's understood that it's going to have a base of 10. If I have a base besides 10, then I need to go ahead and find that log AB. Okay, so base of 5, and then go over, and we said 125. So the reason that I had a clue that this would simplify to an integer, just a plain integer, is that 125 can be written with a base of 5. And so that goes back to those inverse properties that we saw. And sure enough, I get 3. So now I will replace log base 5 of 125 with 3. Because remember what this is saying. This is saying 5 raised up to what number if I had this set to equal? 5 raised up to what number would be 125? Well, 5 raised up to 3 would be 125, so that's why the number is 3. Or that's why it's equivalent to 3. Then on the other one, log base 5 of x, well, 5 raised up to what number would be x? Well, I don't know what x is, so that's why that one stays put. Now going back to the last slide, we could say, well, why didn't we do that here, right? Because we have a 10 here. Well, I could. I would definitely still put in my calculator if you're not familiar, like which ones will give you nice solid integers and which one will not. But 10 raised up to what power will give me 3? Okay, that's going to be something funky, right? And so sure enough, watch. Oh, I could have used the common log, sorry. See, so I get this really outrageous number. I'm going to show you with the common log. I could have just done that. Okay, but I still get that outrageous number. Well, if I don't get this nice integer, then I know, okay, I can't simplify that any further, and I just leave it as log 3. Oops, I erased a little bit more. I just leave it as log 3. All right, so that's why we took log base 5 of 125 down further, because when I punched that in my calculator, it gave me a nice solid number. Something to look at is if this is, oops, just erasing stuff. If I have numbers here and here, then go ahead and punch it in and see what you get. If I have a variable there, then I know, okay, I don't know what that value is. So, all right, they want us to use properties of logarithms to expand the logarithmic expression as much as possible. Where possible, evaluate them without a calculator. We're just going to go ahead and practice it using the calculator as well, but I'll show you without the calculator after we punch it in the calculator. So it's a common log, right? There's no base there, so I understand it to be 10. So log 100,000 plus log y. Okay, this variable, I know that I can't take it down any further. But this, I'm like, okay, I definitely could possibly get a nice solid integer. So let's see, log, and it's 100,000, and I get 5. So log 100,000, the entire thing, probably one of the more common mistakes is that people will then write log 5. Well, log 5 is not equivalent to 5, right? Make sure that you understand that log 100,000 is equal to just 5. So that would be our answer. But I wanted to show you by hand how that works out. So let me write this again over here. So we expanded it, and then we go to simplify. Remember, there's a 10 right here. So that means that if I'm able to express this value with a base of 10, then I can use that, the inverse properties. Well, 10 to the 5th power is 100,000. So I can say, okay, this is now just 5. And if that's not making sense, you'll want to look at 4.2, part 2, I believe it's in. Okay, now we're going the other way. So we use that property to expand. Now we're going to use it to condense, right? So this is how I help to remember the difference. I have one log, right, showing here, and they're telling me to expand it. So I'm going to go from one log to multiple logs, which I did initially when I expanded it, but then my log of 100,000 simplified to 5, right? But when I expanded it, I went from one log to multiple logs. Same thing on this one and on that one. Now I'm going to go from multiple logs to one log. So remember that this is our natural log. ln is the same as log base e. But I'm going to go from multiple natural logs to one log. And that product rule tells me that if there's addition between those logs, that I can have multiplication on the inside of just one log. I put the 20 before the x because, standardly we put the coefficient before the variable. Okay, let's see this one down here. So now we have a common log, natural log. I specify that one in my brain. I think ln, those are the first and last letters of natural. I know they're backwards, but that just helps me remember that's my natural log. And then at the bottom, the common log, those logs don't have bases. So I'm like, oh, they all look so common. So that's just a silly way to remember it. All right, so 4 times 25. Now I'm going to simplify that, right? Up top, I couldn't simplify 20x anymore, but I'm going to simplify that to log 100. Okay, but am I done? I'm not, right? Because remember we said, okay, if we just have a value right here, then you'll want to at least punch it into your calculator if you can't identify what you would be able to simplify it to. But remember, there's a 10 right here. So if I can express that 100 as an exponent with a base of 10, which I can, then I can knock this out and my answer would just be the exponent. Now let's say that you're here and you're like not really being able to identify what your base could be. Okay, so I would just put log 100 and look, it gives me 2. Okay, logarithmic property number 2, the quotient rule. So let's think back to what our quotient rule was in when we were talking about exponents. So the quotient rule said, if you have the same base in a quotient, then you would do subtraction between the two exponents, right? Well, it's correlated because remember, exponential functions are inverses to logarithmic functions. So same thing here, well, similarly here, we see that if you have the log of a quotient, then it's going to be the difference of the individual logs. So we have log base b of m divided by n is equal to log base b of m minus log base b of n. They give us an example down here. I'm going to rewrite it so I can explain it as we write it. I have log of, and this is my common log of x divided by 2. It's the same thing as log of x minus log of 2. Now, I have a 2 there, right? So 10 raised to what power would be 2? I could tell you that that's not going to come out to a nice number, but I would just check it. If you are not that confident, be like, okay, there's just an integer there, so let me go ahead and see if that would simplify. So it's the common log of 2. Let me see if that would simplify to a nice integer that I could replace. And it does not. So I leave it as log 2. The only time I would actually replace it is if I got it like those 2 answers above, a nice solid integer. So let's apply this. Okay, it tells us to use the properties of logarithms to expand the logarithmic expression. Okay, so remember, when I'm expanding, I have a natural log right here. But because I'm expanding it, my initial step should go out to multiple logs. So numerator first, and then you'll always subtract the denominator. But not just the denominator, natural log, or whichever log they're using in the example, and then the denominator. Okay? Now, I've expanded it, but now I need to see if I can simplify it anywhere. Well, look, we said that ln is the same as log base e. Well, look what I have here. I have e to the 4th. E raised to what, right? If I had it set equal, e raised to what would be equal to e to the 4th? Well, it would be 4, right? Now, if you're like, no, not right, watch. If I have ln of e to the 4th, you automatically get the exponent. That's that inverse property. So we get 4, and then let's say that I was like, oh, well, what about ln 2? You could check it. You're going to get a crazy number, so you would leave it as is. And this would be your answer. So after you expand, make sure that you simplify. Okay? So they're asking us to expand. So I know that I'm going from 1 log to multiple logs. There's division here, so I know it's going to be a subtraction between those logs. Log y minus, log 1 million. I'm going to check if I can simplify that log 1 million, especially because this is a common log, so that means there's a base of 10. If I was just doing it by hand, I'd ask myself, okay, 1 million to what power equals, or 1 million is 10 to what power? A little trick here is you can count the number of zeros. And now this only works with powers of 10, but 1, 2, 3, 4, 5, 6. So I'm like, okay, 10 to the 6th power. And so it would just be log y minus, and then just the 6, because that's what log, a common log of 1 million simplified to. All right, now they want us to go the other direction. They want us to condense. So I'm going from multiple logs to 1 log. So the logs I'm using over here is log base of 3. Okay, and there's subtraction happening between the logs. So it's going to be division. Whatever is positive, so this one's positive, right? We'll go up top, and whichever 1 is being subtracted will go at the bottom. Okay, so multiple logs, condensing down to 1. Whatever is positive, this log was positive, but so is this one. So that will go up top, and then whatever was subtracted would go at the bottom. Now watch, if this wasn't in the mix, then I would have the product rule, right? Where if I have multiplication of 2 logs, then it's the same as adding those 2 logs, right? So it would just be that. Log of x plus log of y would be log of x times y. So you have like a rule within a rule there. So anything that's positive would go in my numerator, and then in my denominator, oops, I'm deleting stuff. In my denominator, I would have whatever log I'm subtracting.